Have you ever heard of rivers in the sky? As temperatures rise, these are just one of the extreme weather events that we expect to intensify. As such, my advisor, Dr. Gary Lackmann, and I are evaluating ways that we can better forecast these systems and communicate these results to especially vulnerable populations on the West Coast. Dr. Lackmann has an especially important connection to this region.
I grew up in Seattle, Washington, and in the Pacific Northwest. In the cool season, we would get these heavy rainfall events. Sometimes they would last a couple of days, and sometimes accompanied by warm, windy conditions with a lot of snow melt. And the combination of heavy rain and snow melt would lead to flooding. In the local media, they called these Pineapple Express events because the air mass a lot of times was coming from the vicinity of Hawaii. And so I was fascinated by these growing up. And later in my career, I studied them. Actually, I studied these flooding events. We didn't call them atmospheric rivers, but that's really what they were. And I published a couple of papers on these back in the 1990s, but we didn't call them atmospheric rivers then. Fast forward several years, Dr. Marty, someone who I'd known through professional contacts and meetings for many years, he was working in Boulder, Colorado, and we had some collaborative work there. But then he left Boulder and left NOAA and went to La Jolla at Scripps and started the CW3E, the Center for Western Weather and Water Extremes. And the work they did there really was studying atmospheric rivers and the impacts that they have on West Coast water resources. So I had a student, Allison, Michaelis, who was just finishing up her PhD, and we heard about a postdoc opportunity to work in this group to study things like atmospheric rivers and how they would change in a warming climate. And so Allison applied for and got that job. And because she was, we kept in touch, she was a great PhD student. She got me and Dr. Ralph involved in further discussions. I went out there and gave a seminar. And next thing you know, we were talking about an additional collaboration and some funding for a current graduate student, Greta Easthom. And the goals of that project are to look further into atmospheric rivers and their predictability and how they'll be affected by climate change. So it's a great group to be involved with, the CW3E. It's a consortium that's highly multidisciplinary. There's all different types of agencies involved, government agencies, state agencies. There's private sector companies and firms involved in it. So there's a very diverse set of stakeholders that all contribute to the CW3E. And a lot of them aren't meteorologists or atmospheric scientists. And so in order for them to understand how to use the information and also for them to understand the benefit they're getting for their investment in the organization, there's a lot of science communication that has to take place. And a lot of the employees at the CW3E are really sort of applications-driven, stakeholder-driven scientists, where they're working directly with the stakeholders to make sure that the science that they're doing is in a form that's useful for actionable decision-making. And so science communication is absolutely essential to the whole organization. And if it weren't for effective science communication, the organization probably wouldn't exist. Because in order to get stakeholders to recognize the benefit, you really have to break the science down and let them know how it affects their operations, how they can use it, how they can benefit from being a part of the organization. So there's a lot of emphasis on science communication in the organization, and I think they're planning to expand that even more, perhaps even doing more with social media going forward. An atmospheric river is basically a narrow corridor of strong water vapor transport. So you have strong winds blowing moist air out of the tropics and into the mid-latitudes. And this low-level flow of moisture, it's associated with a jet of low-level winds. And previous research, including some work that I've done, has shown that low-level wind maximum, that low-level jet, is actually due in part to energy released by condensing water vapor. You know, when you have a glass of ice water on a humid summer day and all that water condenses on the outside of the glass, you've seen it quickly warms up your drink. That's because that condensation is releasing a lot of heat. And in the atmosphere, when clouds and precipitation form, a lot of that heat that's released can actually change the pressure and change the winds. And that's one of the things that helps drive these atmospheric rivers. So there's a feedback there where you have the atmospheric river is moving all this water vapor along, and some of that is condensing out and forming clouds and precipitation, which strengthens this low-level jet, and that makes the flow of moisture even stronger. And so when these jets, run into the mountainous west coast, the air is lifted as it encounters the mountains, and the air cools and the water vapor condenses, and you can get very heavy rainfall. Also, because it's warm air, that often is associated with a high freezing level, which means, again, you're getting a lot of snow melt, rain on snow events. So this has big implications for water resources, because if you have the combination of heavy rain and snow melt, then that can give you severe flooding. And so that's one of the impacts, one of the threats associated with atmospheric rivers. In a warming climate, you would have a further increase in freezing level, but perhaps more importantly, the amount of water vapor in the air goes up strongly as the temperature warms. So it's possible, and we need to study this to find out for sure, but it's possible that future atmospheric rivers would be even stronger and give you even more extreme rainfall and snowmelt conditions. And if you get into a situation where you have a lot of snowmelt and the freezing level is very high, the amount of water that's stored in the snowpack in the mountains could decrease a lot, which has huge implications for agricultural interests in places like California. The West Coast, the water off the coast is very cold. And so that doesn't help in terms of serving as a moisture supply. The warm water is what you really need to put a lot of water into the air. And so in the West, to get heavy rainfall, you have to transport the water vapor from far away from the tropics to get it there. And so these atmospheric rivers really have a huge control on the amount of rainfall. Now, if you go into the Eastern US or other parts of the world, say in the Eastern US, you have warm water with the Gulf Stream just off the East Coast, or the Gulf of Mexico never gets that cold. So the water vapor is closer by. So you don't rely as much on atmospheric rivers because the water vapor source is basically right there. You can still get them. And sometimes you get these feeds of moisture coming out of the deep tropics that can lead to intense flooding early in the central and eastern US. There's been studies of that. But because there's other warm water nearby, you don't rely on atmospheric rivers as much in the east for heavy rainfall. Basically, a moisture feed that's accompanied by a tropical cyclone or hurricane or a weaker tropical storm, because sometimes in those really warm tropical air masses, you can spin up a tropical system. But you look at what's happening in Lake Charles, Louisiana, just this week, extreme flooding, record flooding that exceeds what they had with their hurricanes last year. And this air, there's a very strong jet of moisture feeding off of the Gulf of Mexico and out of the tropics into eastern Texas and Louisiana that's causing devastating flooding. The city of Lake Charles has had to rescue dozens and dozens of people. There's extreme property damage. And so in a lot of ways, that's an atmospheric river event. Whether it fits the technical definition, I think it would if you calculated it there. But because the West is really more exclusively reliant on atmospheric rivers, we tend to call them that and study them more on the West Coast. But the same phenomenon happens in the East. So Hurricane Joaquin produced extreme flooding in South Carolina in 2015 and early October. And the hurricane was offshore and it never really made landfall. And we were interested in how much the hurricane actually contributed to the flooding in South Carolina. And so we did some computer model simulations where we removed Joaquin, and the flood still happened. So the flood happened in North Carolina instead of South Carolina, but the flood still happened. And that was strong evidence from the experiments that we did that it wasn't the hurricane that caused the heavy rain. There was very moist air in place, and there was another upper level weather system that really caused the heavy precipitation. This map here in red is basically something that we calculate to measure how much the water vapor condensation is affecting the atmosphere. Remember, I mentioned that when you have clouds and rain forming from condensed water vapor, that releases heat. And that heat release creates this ribbon that's shown in red here of something that we call potential vorticity, which is a technical term, but basically that tells us where the atmospheric flow is going to be affected by the result of all this water vapor condensing. And then the blue here basically shows an area of large water vapor concentration in the atmosphere. And you notice that this water vapor is surging up out of the tropics and coming up into the higher latitudes. Here's Washington State, Oregon, and California over here for orientation. So you see this moisture surging up out of the tropics. And on the western edge of that moisture is these red bands, which show this this measure of the condensation. So this is something that we can study with computer models, and we can look at how well the models represent the condensation and how variable this feature is. We know that models don't do very well in predicting the exact amount of rainfall. So that means that they don't do well in predicting the exact amount of condensation and heat release. And so we expect that this feature is not very accurately represented in computer models. And so that's one thing that we're working on, is how can we improve the representation of that feature, which is really what's driving the low-level jet and what's driving this moisture northward. And if we can improve the ability to predict those features, then we can make the model forecast better. And then people, the public and water managers will have better information for water resource management, reservoir management, and those types of short-term decisions. Now, in the longer term, with more water vapor, you would expect potentially you would get more or stronger of these red bands, which could make a stronger atmospheric river. And so we can take a setup like this and apply warming and see, well, how much does it change these features? And that's what Greta Easthom is working on. One of the things she's working on for her research is to study that and simulate future atmospheric rivers to see, are their dynamics different? Is their predictability different? And that will help us anticipate what types of changes are coming for atmospheric rivers. It helps to have observations and to put those observations into the weather forecast models so that we can make better forecasts. And so there's a team of people, and it involves NOAA and the Air Force and the CW3E people, and they fly various aircraft out into these storms when they're still offshore, and they launch what are called dropsondes, which is basically an instrument that takes a profile of temperature and wind and water vapor that they drop from the airplane that fall down through the atmosphere and measure different quantities. And then that helps improve the sort of starting point in the weather model to have a more accurate handle on the way things are. And then that leads to better forecasts down the road. And getting these observations is really critical. This program has been going for several years now. It keeps getting bigger and bigger. And they can test the weather models and say, well, how would the model have done without those additional data points? And then how much does the forecast improve when we add those data points? And what they've shown is that there's a large improvement from adding those data points.
Another feature used to capture the intensity of atmospheric rivers is called the Integrated Water Vapor Transport, or the IVT, which is the total amount of water vapor transport in an atmospheric column. These values can range from 200 kilograms per meter second to 1,600 kilograms per meter second.
So I've been really impressed with the leadership and the organizational structure of the CW3E, because you have enough critical mass of people at different stages of their careers to have a really wonderful work environment and an environment for learning and collaboration. And so I've really appreciated working with them, because it's a model, I think, of how academic science can be done with a collaborative rather than competitive attitude and mindset. And so it's really been a pleasure to work with them. Very nice people, and they have great resources, and they're doing some very exciting science.